Alright, this video is going to take you through your Desmos activity that we've been working on the last few days. Sorry I'm not there to go over it with you. We will do Fun Fact Friday upon my return. So, go ahead and find your packet. We're going to go through this whole Desmos thing step by step and make sure that we understand what we were supposed to get out of this. The second video will be more specifically about local linearity and what are the main concepts you need to know, not only for Tuesday, but also for the AP test in May. Alright, so step one was typing in y equals f of x, and step two then is when we figured out how to do our slider. So hopefully you came out with typing in the point a comma f of a. And then took your extra step over of h, so you should have a plus h comma f of a plus h. So we're looking like this. We've got our point a f of a, and we've got our a plus h comma f of a plus h. Then it says to let m be the slope between our two movable points. Well, the two movable points are the two that you just typed into your Desmos. So our slope is going to be our y2 minus y1 over x2 minus x1, but we know that on the denominator our a's are going to cancel out, and so we will just have our quotient with an h in the denominator. Alright, step 5 says use m and not the fraction that equals m. So remember, in your Desmos you should have your actual m typed in. We're not talking about this 0.9 right here. We're actually going to use this m, the letter m, as our slope. Using point slope form, we're going to set up y minus f of a equals m times x minus a, and says what is the mathematical term for the line above as it relates to the graph of x. Hint, the answer rhymes with bleakant. This would be the secant. That's what we're looking for. What happens as you slide a? Well, if we look back here. Alright, so if we take a look and see what happens when we slide a, we notice that our line is moving along as a secant line, touching 2 points along our x squared curve. So, next thing then says when h gets really, really small, we say that h is approaching 0. So we know that h can't actually get to 0 because then our denominator is 0. So we would say the limit as h goes to 0 of f of a plus h minus f of a all over h will allow this distance to get smaller and smaller until eventually our secant line turns into our tangent line, and the slope of that tangent line rhymes with schmerivative. It is derivative. Alright, use a limit expression similar to your answer in number 7 with a equals 3 and show the chart that you hopefully found in number 8. So here I'm going to take the limit as h goes to 0 of f of 3 plus h minus f of 3 all over h. But we know from our very first slide f of x itself is equal to x squared, which means when I go through and I apply this function, I'm going to end up with 3 plus h squared minus 3 squared over h. First method to evaluate a limit is always direct substitution. Unfortunately for us, this is going to yield 0 over 0, so we have to keep going. So I'm going to have the limit as h approaches 0 of 9 plus 6h plus h squared minus 3 squared, which is definitely 9, all over h. Doing some cleanup work, our 9's are going to cancel, and h is going to cancel, so I'm left with the limit as h goes to 0 of 6 plus h, which really will be equal to 6. Alright, now this one says to keep our x in the expression, so instead of replacing my a value with a 3, we're just going to leave an x there. So I'm going to have x plus h squared minus x squared all over h. Again, 0 over 0 means I have to keep going. Alright, so now when I go through and I do my cleanup work, my x squareds are going to drop out. There's an h in every term. So I get this brand new blue limit problem. The limit as h goes to 0 of 2x plus h. So as h approaches 0, this whole expression is going to simplify to 2x. Alright, so going back to Desmos, it says to find the exact value of f of 0.707. So if we jump back here, you can, if you would like to, type in the point 0.707, comma, I need to take out the full keyboard. There it is. So 0.707, comma, f of 0.707. Oh, this was after we had lowered our function by 4, which hopefully we noticed we had the same slopes going on, and you can prove that to be true as well from number 10. This had some random typing in it. Alright, technical difficulties. Please stand by. And we're back. I have my 0.707 and f of 0.707 appears to be negative 3.5. AP is going to require 3 decimal places, so if possible you want to do that, but obviously here we don't have those to carry out. It says we'll use a new secant line to approximate this. We want to find a decent interval. Well, if I want to know what's going on at 0.707, I probably don't need to be looking, between like 30 and 38. So I'm going to choose the interval of 0 to 1. And so thinking about 0 to 1, I'm going to let A be 0. And I'm going to let h be equal to 1, so we take a step of 1 out to the side. You might have a different interval. That is totally okay. Don't panic. But hopefully your graph looked something like this. And you saw this purple line right here. And this purple line is going to overestimate what's actually happening along our black curve. So the secant line will over-approximate because it is higher up on our y values the way our graph is curving. Alright, it says we're supposed to write the equation of a secant line using L1 as our notation. So what this is really saying is you can start with point slope form. L1 of x minus, one of my y values was negative 4, equals my slope of this line is 1, x minus 0. So the point I chose was the 0, negative 4. That might be different for you, and that's okay. But if you go through and you isolate L1 of x, because that's what Mr. Lakin is asking for right here, we're going to end up with 1x. Then this would have been a positive, so we swing it over, we get minus 4. So now if I take 0.707 and plug it in for my x value, where's my graph going on? So if we find 0.707, you can plug it in. I just don't have a calculator with me. We get negative 3.293. And negative 3.293 is in fact greater than our f of 0.707, which we were hoping for. Alright, so thinking about a tangent line. So if I think about this, and I drew a tangent line here through A, or if I drew a tangent line here through my A plus H, those tangent lines are going to extend, and they're both going to end up being too low to estimate, in which case our tangent approximation is going to be less than our actual value. And this is something that's going to be important for us. We're going to use local linear approximation when you can't actually know what the function is doing at a specific point. So that should take you through your Desmos activity. There will be another video posted about local linearization overall and what to take away from it.